All right. Today we're going to talk a little bit about big O notation. Has anybody heard of big O or like time complexity or anything like that?
I've heard of it, but definitely have zero understanding of what it is.
Okay. Anybody else?
Yeah, I learned about it during my computer science bachelor's.
Yep. Yeah, you definitely would learn it there. Of course. Anybody else? Just curious. So, what is big O? Yeah, like what is big O? Does anybody?
Basically a way to tell how long your program takes to run.
Yep, it's essentially just how efficient and how much, yeah, exactly, how much time it takes your program or algorithm or function to run. Yep. So it's how well your algorithm's performance is affected with a change in the size of input. So, you know, if you have like an array of one element, and in order to grab that element out of that array, it's pretty easy. It's just like, all right, I just grabbed the very first index. Now, if that array is, you know, 1,000,000 lines long, or an array that has a size of 1,000,000, and you have to search or like find a specific element within that array, you know, it can, if that element just happened to exist at the very first index, hey, it might not take that long. It might just be like one operation and you're done. Otherwise, like it can take 1,000,000 operations before it's done. That's just one quick example. So again, algorithmically, it's just about like execution speed of how fast your function executes based off of a change in input. I'm just gonna kind of go over some examples as well. So big O notation, N is just literally the size of an input. O is literally just a symbol, basically from complexity theory and computer science, blah, blah, blah. It's just a bunch of stuff. But if you ever remember back in like, I don't know, algebra, like f of x, that's kind of like f of x equals or f of y. It's very similar. And it doesn't have to be N specifically. It could be any variable named A, B, C. It's just, that's just the way this big O notation is written. All right. And there's different time complexities or different time complexities. There's O of 1, which is constant time, which is like no matter the size of input, it doesn't change how fast the algorithm runs. So for an example, we'll go over an example where like logarithmically, it takes, there's like a lot, or I don't want to say a lot, but it executes it several times and then it like trails off. And I don't know if you remember like algebra, like what a log graph looks like. It goes like, whoop, and then like trails off. Something like this is like binary search. So it like continues the breakdown. Your problem continues to get smaller and smaller. O of n is linear time. N, log linear time, quadratic time, n squared. That's usually not good. Those are generally nested for loops. You'll see that a lot. I know a lot of times it's like, oh, I need to do a nested for loop. And then there's exponential time, 2 of n. Obviously, the faster the algorithm, slow. So let's just kind of go through. So big O notation, constant time. So for an example, here's an input. So the operations is on the number of operations and the size of the input is on the X. So for example, accessing a very single element within an array or accessing an index in an array. Now, it doesn't matter the size of the array. You're just accessing an index. So that's constant time. It always will just take one operation. I think I kind of mentioned this. Logarithmic time. So the graph kind of goes up and then it like slowly trails off. So it doesn't take that many executions. So for example, an input of 250,000 there's not that many operations for that one. N log or linear time, it's just like linear search. Do you remember the linear search problem a couple of weeks ago? You literally just loop through an array until you find whatever element you're looking for. So if you think of O of n is linear search, a single for loop. So a for loop, I would say, equates to O of n. N log n. So generally you'll have a for loop in some sort as well as log n. So when you're looping through something and then you have another operation that gets smaller and smaller. That's n log n. So merge sort is one of those sorting algorithms. N squared, finding duplicate values in an array. So a nested for loop of the same array. So I know a lot of times that's kind of like a brute force method. You just got to do nested for loop. If I needed to find duplicate values, just do a nested for loop. And that's generally not that great. There's probably a more efficient way to do that. And then exponential time, finding the nth value in the Fibonacci sequence. Yeah, you'll rarely ever come across this unless you're doing like specifically a Fibonacci sequence type of problem. I know these graphs don't really do it justice. Like how do like that one and this one kind of look very similar. But here is a really good chart. Find this online. As far as the time complexities of constant time, log n time, O of n, n log n. Now this graph isn't specific. It isn't what is it called? Scaled correctly because obviously constant time O of n is linear time, which if the graph was actually equal, the number of input operations, X and Y axis size were equal, it would look like go across the middle of the screen. But there's just
N factorial.
I'm sorry?
This would added n factorial. That's pretty nasty.
Yeah, I didn't even add that one because that one's,
Can I ask a question about Big O?
Yep.
I know that you had, I believe if I remember, you have some experience like working in the financial industry as well. Is there any kind of situations like notoriously that weren't really like where Big O, I mean, was like kind of in the worst case scenario as you?
I personally don't have any experience with that. I know Ankur worked at a trading firm, so Ankur would be able to speak more to that.
Sorry, what was the specific question? Like dealing with, so I could just say, so Big O is more just like conceptual. You're not usually doing it as a coder, like you're not applying it directly. It's just more of a mindfulness of, hey, you have an algorithm, how's it going to perform as data changes? And then knowing, like, again, as Tom mentioned, like if you have something that's n squared, sometimes you might not be able to get away from that, like that complexity, but just knowing that you have something that's n squared, then you might be like, all right, I know the worst. So this is the worst case for any algorithm. Mm-hmm. If you notice something's n squared, then you might be like, all right, how can we optimize this so that, in most cases, it won't be that level, like the worst of the worst. So optimizations are kind of tied in with complexity analysis, but that's probably a separate lecture.
Yeah. Again, yeah, we'll kind of go over like that as well. But yeah, this is always the worst case scenario for your algorithm. Because as I mentioned before, with like linear time, like it could be just one. You might just happen to do one operation and you find it, or you might happen to do worst case scenario, whatever the size of the input is, which would be really bad. I was going to say something else, but I forgot. This stuff does come up in interviews. So this is more of also for interview practice. They'll be like, hey, what's the Big O of whatever algorithm you wrote? And you'll have to like kind of discuss what that is, and we'll kind of talk about kind of how to calculate that. So data structures, here's another, well, I'll Slack out a link to this, but these are the common data structures and operations. So I know when Sophia was talking about data structures, there's benefits and drawbacks to every data structure. Some are good for some things, some are not that good at doing one other thing. So it's all about using the correct, not the correct data structure, but the data structure that it works best for a specific scenario. So like an array, to access it, it's really easy. It's constant time. To search through it, it's O of n. You can kind of see the benefits and drawbacks to all of those. Yeah. So
Theta in the average and O in the worst, just to confuse us.
So, I'm sorry. Yeah, I actually don't know why they do that. Because it would just be the worst.
They're using the theta symbol rather than O in the axis columns.
Oh, yep. No.
That might just be the standard. So like you use like theta for average access, and then you would use big O for worst.
But let's actually kind of jump into this and kind of just show you some examples. Where'd it go? So I'm just going to copy over some like an array. So if we talked about constant time, let's go back. Constant time. So like def constant time. Whoop. Data index time example. If I wanted to grab an element from the data and just return it, so I can say like return data.idx. That's constant time because I'm just typing in an index and I'm literally just extracting that value from that index. It doesn't matter if this is, 10 has 10 elements in it or a million elements. It's just accessing an array by its index. So this would be O of 1. And let's talk about linear time. Find item greater. So I've got data and item. So this takes in an array and an item. I can say for element in data, if element is greater than item, I'm sorry, if item is greater than element, then return element. And then if it loops through it and doesn't find anything, returns none. So this for loop. So what would, I think I already said it. What would be the O of n of this item? If I look right here.
Just O of n, because it's just one for loop.
Yep. So if data is like 1, 2 elements long, it'll only have to go through the for loop twice. But if the element was, like a million or 10 millions, it would have to go through it 10 million times as a worst case scenario. So again, this is the worst case scenario. So this is linear time. So this would be O of n.
That's not actually worst case because it has to go through the entire list to.
Oh yeah. to, yeah, so this is the worst case scenario. Because no matter what, it would have to go through the entire list. It's not returning at,
That's the only case, actually. I mean, if you're dealing with worst case, it would be like if you're looking for an item equal to 24. In some cases, it would only have to go a little bit through the loop, and another would have to go all the way, which would be the worst case.
yep. So, yeah. All right. So anytime you're dealing with like for loops in an array or any for loop, it's always going to be O of n. Let's talk about quadratic time. These are like the main ones. So if, again, quadratic time, O of n, find duplicates in an array. So def find duplicates. So you just have a data, and for data 1 and data, and then for data point 2 in the same list, if D1 equals D2, return true, else return false. Or I can just even say return false at the end. So if we're dealing with two for loops, so one for loop here and another for loop here. So when I'm at like index 1, it has to loop through the entire array here. When I'm at index 2, again, it has to loop through pretty much the entire array, keep looping through. So for every one loop here, it loops through here, or essentially for each index in here, it loops through an entire array. So this would be O of n times n, because if if there's one loop, one for loop is n times n would equal O of n squared. And that's only if they're in the same list. So if you have a nested for loop that's looping through the same list or the same array, it'd be n squared. But what if there was like, we have data 1 and data 2. These are two separate lists. Data 1, data 2. What would this one be? If we had two different lists. Actually, I'm just going to go back.
Would that be 2n, which would be basically equivalent to n?
No, so
That's O to the 2 to the n.
So we still have a nested for loop, but one is going through one list and one is going through the other list. It's very similar to just O of n, but again, n accounts for one input. So this like input, whereas another input, we don't have to call it n because n already is represented by data 1. So it'd literally just be like n times m or something like that. So that it's very kind of similar to n squared, but it'd be like n times m.
So in a big list for the original find duplicates in a single list, if we sorted it efficiently first and then did it, it could be lots faster.
So are you saying if we sorted this first? Was that your question?
Yes, I think some of the quickest sorts faster than the double loop.
Yeah, no, yeah. So if we had to find duplicates, if you sort a list, so that's a good point that you brought that up. So if we have, just throwing other stuff out here. for example, if we had, not find duplicates, but like some other.
Well, if we find duplicates, we only have to go through the loop once after it's sorted.
Right. So if we actually ended up sorting it, but yeah, I'm not going to go into that one right now. But that brought me, I'm glad you brought up like, so if we like data equals, I don't know what that is. Is it data, something like that?
It's either sorted like that or data dot sort.
All right. And just in theory, we like do some logic here. Like that. All right. What's the runtime of this? So we know that looping through is O of n, like down here. Does anybody know what the O of n of the method sorted is? I don't know.
Should be easy to search.
Right. Yeah. But like, that's just one thing to consider is like, you have to consider what the O of n is of built-in methods.
Is there an easy reference for that for Python for all the built-in methods? Or
I have not found one. And in fact, like sorted might actually use two different sorting algorithms. Like it might be like, all right, if the array is only 10 elements long, we'll use some sorting algorithm. But if it's over 10 elements long, it might use another sorting algorithm because it's like, it doesn't take that long to sort it with 10 elements. But anything over 10, maybe another sorting algorithm is more efficient. So some of your built-in methods might use different methods depending on the size of the input. All right. All right.
Sorted is apparently like an n log n, but maybe a little bit faster for most like real world data. Okay.
Gotcha. So there are some things to consider. I think so if I had def 2 for loops and I did like data 1, data 2, these are supposed to be 2 for loops. I say 4 elements in data 1, do something. And then outside of that for loop, I do 4 elements in data 2, do something. And then return. What happened here? So what would be the O of n of something with 2 for loops, but that aren't nested?
it would be 2n, which would be equivalent to n. So the same. Cool.
So we have O of n plus another n. So we have 1 for loop, which is O of n, plus another for loop, O of n, which equals O of 2n, but with big O, big O and time complexity, it doesn't really, like this other for loop doesn't really isn't that substantial. So we drop the constant. So it just be O of n. So you want to drop constants. So for example, 2 separate for loops of the same array. Or just 2 separate for loops, not nested. Again, also you want to use worst case scenario. So for example, if we had element in here and then we said like element dot index. I don't know what the, is it index? Data. I don't know if that's the correct syntax, but maybe here's one for loop, I'm doing something, and then in the second for loop, I want to find the index of where I'm at. So is this the right, what's the right syntax to find the index?
I think you flip it and be the array dot index of whatever you're looking for.
All right, so element. So if I wanted to find the index here inside this for loop, what would I have to first do? So what would be the O of n of this? So we're up here, we have O of n for this first for loop. In the second for loop, we have this other one for loop. So we have O of n, but what's the time complexity of finding an index? The like where an index is. Is that O of n? Maybe. So this would be essentially a nested for loop. So this one would be times n, which again would reduce to O of n squared. So we have O of n squared down here and O of n, but you want to take the worst case. So the overall algorithm would be O of n squared.
But they're not actually nested.
This one down here, this built-in method, it probably loops through the entire index or the array.
Yeah, right.
Yeah. So yeah, you just gotta kind of be conscious of built-in methods, where they are and what the time complexity of those are.
Yeah, index is O of n according to Stack Overflow.
Okay, awesome.
So what happens if you're going to do something like read a file or something along that line, which takes a lot more time than peeking at something in a list?
So what do you do if you have to read a file versus?
Well, if you're comparing complexity of two algorithms and they're both doing the same thing inside the loop, then I can see comparing them. But if one of them is doing something simple and one of them is doing something more complex, is it still just O of n?
Yeah. Yep. And if like, yeah. Let's talk about binary search and linear search. These are both two challenges that binary search. So what was linear search? What was the O of n of that? Does anybody remember?
O of n.
Linear was over.
Yep. All right. So we're just going to run through some operations to see how many operations this one takes based off of. So I've got some list comprehension. So right here on line 12, I'm just creating an array of 10 and say the worst case scenario, I want to find where index of 10 is. Python. I'm just going to run this, just see if it works. So the number of operations is 10, obviously. Now, also, if I was searching for one, I think it might be 2. Number of operations is 2. But if we didn't know essentially the worst case scenario, it would have to loop through it 10 times. Likewise with of 100, or I'm sorry, an array of length of 100, if I wanted to find the very last element in there, the number of operations is 100. Again, it scales linearly. It's O of n. So the worst case scenario is that I'd have to loop through this thing all the way to the end. Now let's talk about binary search. We kind of went through that as well. I'm just going to bring that operations in here. So this is binary search. I'm just calculating the number of operations. Let's see. And does anybody remember what binary search is? The
Log n.
log n. So I have an array of 10. And for example, I probably should just randomize it, but it doesn't really matter. So in here, so I've got an array of 10. It's sorted. And we'll want to search for the number of 3 in it. So if I do binary search, so number of operations is 3. Let's increase that to, let's actually just do them all. Whoop. I guess I can't. So if I'm looking for 3 with an array of 10, it took 3 operations. Now, if I'm looking for, let's do 3 again, in an array of 100, it only took 5 operations. So if I wanted to look for 3 in an array of 1,000, it only took 8 operations. So notice how as the input size scales up, the actual number of operations is starting to, so it's 3, 5, 8. Now if it's 10,000, clear, 13. So it's not increasing as much as the number of inputs are.
I have a question about log. So basically, because this is what log base
2.
2.
Yep.
Now, is anything considered log n? Like, say you have a nested for loop, but the second for loop in the nest, or the second for loop, takes whatever's left. So it's getting smaller in the same way that the higher you go up, the smaller the set gets, but it's getting smaller a lot less than this.
Yeah, I think that's n times log n, like log linear. And
Okay.
I'm pretty sure that that's that merge sort. So
Okay.
yeah.
Okay.
But yeah. So you can kind of see as log n, the more inputs I'm inputting, it's slowly it's not increasing as much. So I can even, I don't know if 100,000 would work. Might take some. So look at, it only took 15 tries again. And how much of that one?
13, I believe.
Yeah, 13. So it's not increasing that much at all, the number of operations, yet our input size is increasing by a factor of 10. All right. Does anybody want to see? This one, Fibonacci, how horrible it is?
For science.
Let's do it.
All right. So here we have the Fibonacci. If you don't remember, the Fibonacci sequence is the next number is the addition of the previous two numbers. So this is finds what value is at what element in the, so at the first element, like what's the first number in the Fibonacci sequence. So if I did on fib, see the input value is 1, the Fibonacci value is 1, and the number of operations is 1. So let's increase that to 2. So, all right, not bad, because we have some test cases here, some if statements. This is, hey, if value of 1 or 2, it only has to do 1 operations. Now let's look at 3. So we had 1 before for 1 and 2. So now we're at 3 operations. And now we're at 5 operations. Now we're at 9. So we're gradually getting more and more by one input size bigger. So we went from 5 to 9. Now we're at 15 for 6. So you see how it's 25 at 7. Let's just go to 10. Let's see how fast that goes high. So we're there at 109 operations when we're at the input of 10. So it's almost a factor of 10 slower, or yeah, slower. Now let's do like 15. Look at 15, we're at 1,200 operations. Let's do 25. So we went from 15, input of 15 to 25. Number of operations will go from 1,200 or 1,219 to 150,000, 49 operations. Keep going up. See what 50 would look like. I wonder if my computer would crash. Yeah, it probably crashed. See how long it takes. It probably doesn't even have a number that big. I don't know.
So I was looking at, there's actually a Code Wars challenge, and it was refactoring Fibonacci to use recursion once and use a memory list to go on the top. I thought it was a pretty interesting one.
Wow. Huh.
Looks like it'd be 1 times 10 to the 15th.
I'm sorry, say that?
Your 50 looks like it'd be 1 times 10 to the 15th operations.
1 times 10 to the 15th.
Quadrillion.
Yeah. There we go. 1,664,000. So it's drastically increasing the number of operations with a small input increase.
I was surprised that doesn't blow the stack.
I know. Anyway. But just some things to consider. Just remember, drop constants, 2 separate for loops of the same array, 2 of n. Drop the constant n. Always use the worst case scenario within the algorithm. Just things to consider when writing functions. You know, searching through dictionaries or objects are faster than searching through lists or arrays because objects don't keep track of indices. So when in doubt, use an object. Wherever possible, avoid nested loops. It's not always possible to do so, but try to avoid nested loops. And if you write some poor big O or write some poor O of n squared, more often than not, there's probably a way to refactor to make it more efficient. Always get it to work first, whether it's nested for loops or whatever, but there's more often than not, there's a way to make it less than O of n. I'm sorry, O of n squared.
So quick question with the Fibonacci recursion led to that many operations, but as far as binary search was use that with recursion. And so it's not necessarily the recursion that's making this bad, it's just how the operation flows.
Correct. Yep. So, and if you ever enter an interview and you write O of n squared, there's probably a more, like I said, there's probably a more efficient way to solve it. And that's probably what the interviewer is looking for. But first and foremost, solve it first, just so you can make sure that you know how to code it, like code the answer. Again, getting the right answer is like first and foremost the more important thing, but then go back and refactor it to make it more efficient.
Now, would you suggest like if like functionally on the job, if we know that a data set is going to remain relatively small, will it matter too much, or do you always try and optimize to the fullest extent?
That's where questions would come in during the technical interview. You'd be like, what's the maximum input value should this be? And they'll say, oh, the maximum will only be 10. Then you can optimize for that input. But more often than not, they'll say it can be an infinite or like a big int, like it can be 1, negative, or it can be 1,000,000. So at that point, you'd be like, all right, now I have to optimize for the worst, like optimize for efficiency.